one of the factors that I already mentioned is the part price, right? So if you're trying to make your part at a cheaper price, then high pressure die casting is something you should explore. The second thing is production lead times. So even though the die will take you about 2 to 6 months, the second the die is ready, you can expect weekly, monthly, kind of even daily production of that die. So we would go from, say, I'll give you examples at a later stage in this presentation, but that's one of those things. Production becomes significantly faster. The next is part consistency. Now, with any other process, you might have some form of variation. Even with machining, you might have variations in tolerances here and there, but with dies, you will get a consistent part every time. So, and the same can be expected throughout the production. So that's not a challenge at all. The next one is about optimization. So, with since this is a pressurized molten metal that is pushed into a cavity, a lot more possibilities are there in terms of optimizing your part. So any kind of weight savers that you can add, any kind of improvement in design that is possible. I'll show you an example at a later stage in this presentation. But optimizations are also something that you can consider. One of them being part consolidation. So the components that are attaching to the component you're considering can also be integrated into a single casting. And the final reason why you should consider is environmental benefits. It's just a better process in terms of environmentally. Also, it gives you a significant advantage in terms of lightweighting your component. So just overall environmentally better uh, in that sense. What all you should consider when you're for your component. First thing is your annual quantity, or if not, your project quantity. So your project might last over a period of 3 years, 5 years, or even 2 years. So you can predict the amount of quantities you might require over that period, because a die once made can be used um like next year again, and the year after that again. So it will survive, right? So consider the annual quantity or the project quantity, and that should try and figure out whether you're able to meet the break-even points with those kind of volumes at least, right? With the savings that you might have with those kind of volumes. So the next thing is part geometry. Not every component can be die casted. There are ways of solving problems of geometry, but not every component is obviously die castable. So this is part of our major discussion with your team, is understanding the geometry, what features are important, what features are added for other aspects. One moment, sir. One moment, please. So sorry, I'm taking this call from home, so that's for better internet. Anyways, let's continue. So part geometry we've covered. I think the next part that you're considering is surface finish. So um, as you saw from the previous pictures, the surface finish is quite smooth. You'll get a shiny finish based on what you want as a surface finish for your coatings afterwards. We can do sandblasting or shot peening or heat treatment, whatever you need. That's something that we can discuss with your team during that. Any kind of specialized drawing notes in terms of end use, we discussed that. Property requirements. So there could be times where, say, you're looking at thermal conductivity or mechanical properties, and that might not be possible through a die casting alloy. So we try and understand the properties that you're looking at, and that be achieved through die casting. Other joining components to figure out whether part consolidation is possible, and discussing all the secondary processes post casting. So you might have engraving, or you might have coatings, you might have machining, you might have sparking, any kind of post casting operation that additionally is required for your component to meet the fit form function. That is discussed, and because all of this will add up to your final part price. So and that matters. So if the secondary operations are becoming too expensive, that might also be a deterrent for you. So we'll discuss all the secondary operations that are required for your part, and then that's another discussion to have. So when is the right time? The most important factor to consider is the design stable? So if this is an evolving design and you're expecting that this design will constantly evolve over the project course of the project, then maybe not die casting. Die casting may not be the right option for you, because once a die is made, you're kind of stuck with that die. Yeah, and though you can make alterations to a die, it is not recommended. So that's the first factor. Is the design stable? The second is, will volumes increase over time? So will your volumes over the period of the project, like 2 years, 3 years, will they continue to increase, and can you benefit from that increased volume? That's a discussion to have. And the next thing is, how much longer is the project life? So like I mentioned this earlier as well, like, is it just for the next 6 months, next 1 year? Then it might be more difficult to meet that break even point. But if it's going to extend for a couple of years at least, then you might have a better chance at meeting that break even point as well. Can you benefit from part geometry optimization? This is something that I think your team could consider, and we could help you with this as well. So when not to consider, volumes. So even when you consider the annual and the project timeline volumes, you're not able to justify tooling, then it's a straightaway no. We can help you with this. Is not too difficult to evaluate. Once you know the die price and once you know your volumes over the period of the project, you can do a simple calculation to figure out at what point will you start making uh, start benefiting from going into a high pressure die casting process. So after 6 months of continuous production, the die is paid off for, and now it's just profits for you, right? Considering an alternative process you would have gone for. For example, if you were going for 1,000 rupees, you were spending in machining, and then suddenly in die casting you're just spending about 100 rupees. So very quickly you'll meet that break even point and start making like it start makes a lot more sense with even little volume. So the second factor not to consider is when the properties that you're looking for are not possible through a die casting alloy. I covered this a little bit earlier. So that's another factor. So one that we recently went through is that ZM21. ZM21 is a magnesium alloy, which is which has better thermal properties than most aluminium alloys, but it's only a rod product. So when the customer wanted it in die casting, we could not offer that because it doesn't die cast that well. So these kind of things happen, and that's something that to consider for yourself as well. The third is if application mandates the realization of the component through rod product. So this we see a lot in aerospace, where there's a manned airborne mission or airborne product, and those have very high regulations as to they don't accept any level of porosity, even the level of acceptable porosities in castings, because every casting would have some level of acceptable porosity. But some airborne systems do not accept. They have a zero porosity standard. So those would ideally directly be eliminated, those use cases. So let's move on to conversion examples. I'll give you 3 examples. So this is a cricket helmet made out of magnesium grill. So this is a picture of ICC testing that it was undergoing. This is a customer of ours. It was originally made out of steel, and through extruded rods, it was welded together. It had after bending and then welding. So they were dependent a lot on skilled manpower, very technically skilled manpower internally. They also had this assembly to get done. Productions were slow, all of that. But when they moved to high pressure die casting, we considered magnesium as the option for this. We were able to integrate the whole component as a single piece, the grill I mean. So there's no multiple rods that are being welded. It's just a single component now. It reduces their production time significantly. The price of the part also drops significantly. There's a significant reduction, and there's also a reduction in dependence on skilled labor, specifically for welding of these things. So so part consolidation, reduced price. It's aesthetically better looking according to them, and also it's a stronger design. So since this is not a welded component and this is a single unit, a single piece, it has a higher strength, and that was proven through the testing as well. Usually, cricket helmets can withstand up to 2 shots in a test situation, and this was able to hold up to 7 shots, 7 hits on the grill. The second example is through gravity casting. So this is a component for aftermarket automotive components. We are giving this to, I think, to in Europe somewhere, and so we were originally making this out of gravity casting and machining a lot of the sections later. There's a bearing section in the center that we had to machine. Obviously, this whole thing was being through CNC turning and everything. There's a significant amount of machining to cut down the additional added allowances that were added during the gravity casting process. But after moving it to high pressure die casting, we were able to reduce the cost. Obviously, we get a net finish, so there's no other machining apart from the bearing machining in the center and the holes. The holes are always done later. So, and there's increased production. So earlier, for doing about 200 units, it might have taken us maybe 3 months to do. And we would have taken 3 months time, figured out how to schedule and do all of that. But now this can be produced in just 3 weeks, 4 weeks. The whole quantity is finished, and we dispatch it. So with the machining included.